Nice. So our first thing is limits. I'd like to jump around in chapter 2. So I don't start in 2.1, 2.2. I teach you how to do limits first, then I go back to that, okay? But it's certainly okay for you to be reading 2.1, 2.2, 2.3 right now. So please do that. Read. Read the book. If you don't know how to read a textbook, I'll teach you. You've got a piece of paper and a pencil or whatever you want to write with, and when you get to examples, you do the problem, right? And then hopefully you'll be able to fill in they'll skip steps. Hopefully you'll be able to argue what they did, right? So that's the easiest way to read a textbook. Start writing. So limits, we're going to talk about numeric limits. Geometric limits, graphical, algebraic limits. That's where I like to start because that's the one I always test on, okay? And then we'll check numerically and geometrically. So when you take that first quiz, you'll know it's right, which is great. Same thing with the test. I teach you how to check everything. The hard part is to not panic when you're wrong, right? If you realize you're wrong, you made a mistake, and then you start to panic, it's over. So we want to talk about an informal limit and then our formal limit. So let's talk about numeric limits first, because they're the easiest to deal with, right? Well, I should talk about the notation too, but that's fine. So let's say f of x is something simple, 2x minus 1, right? We can certainly look at that. And then I'm going to be asking for the limit as x goes to 2 of f of x. Anybody know what the answer is? 3. So what is a limit is simply the height. And it's a predictable height. If I can plug in, it's obviously predictable. Right? If I can just plug in, do it. That's the key. So when I'm trying to do limits, the first thing I'm going to do is plug in the value to the function, right? So this is my value. I want my x to get close to 2, and then we'll figure out the height of that. Since this one I can just plug in, right? So the limit will always be an answer, right? No, sometimes limits don't exist. Sometimes limits don't exist. We like to say DNE does not exist. Yep. So, like if I look at the limit as x goes to 0 of the absolute value of x over x, this one is a DNE. And again, if we look at it graphically, remember, where am I trying to predict my height here? At what x value am I trying to predict my height? At x equals 0. As you can see, the problem, if I'm here and walking this way, my height's underground, right? And if I'm here walking this way, my height's above ground. So the question is, at 0, am I above ground or underground? Can't tell, right? This is the same thing. You have a grandparent with a basement with a light on a string. You know what I'm talking about? Right? You click it and it goes on, and you pull it again, it goes off. If you do that an infinite number of times, is the light on or off? No? I know the answer. I want to be able to predict where I'm going to be in the future. Right? So is my light bulb on or off? I do know, it's off. Because you burnt out, right? You know, so, but anyway, on this one, you can't tell which height we're going to be at, right? So when I walk to 0, I don't know where I am on the graph, but I've got to walk to 0. If I'm walking from the left, I'm underground. If I'm walking from the right, I'm above ground, right? So it does not exist. Graphically, these are both pretty easy to see, aren't they? At 2, I hit a height of 3. At 0, I don't know where height I'm at, right? In fact, you'd kind of say, well, if I could actually get to 0, in this case I can't, because I can't divide by 0, right? Notice there's a hole in the graph down here. There's a hole in the graph there. But when I'm going halfway to the wall, do I care about actually getting to the wall? Or can I tell that I can get to the wall? You know what I'm saying? I'm trying to make a prediction. So this is my informal definition. The limit as x goes to c of f of x equals L, which is a real number, a real height, right? Says that L is the predictable height of f of x as x goes to c. It doesn't have to get all the way there. I want to get real close, okay? I want to get real close. And usually by the time I get to gas station money, 3 decimal places, I can make this prediction pretty easily. And we'll look at one on Desmos right now, if you want to have Desmos open for me. So a numeric limit. So for example, we can do one that's obvious. We want to find the limit as x goes to 2 of 2x minus 1. We already know the answer is 3, but we want to look at numeric limits here. So I'm looking at x and f of x, right? And I want to get really close to 2. So $1.90, $1.99, $9.99. There's my gas station money. Once I get to that gas station money, it will be obvious. In fact, we already know it's 3, right? But let's take a look at what happens on Desmos. I won't ask you for a numeric limit on a test or a quiz, but you're going to be able to check yourself using a numeric limit on Desmos during the test or quiz. So I've got f of x equals 2x minus 1. Obviously, I can plot that point, what was it, 2, 3, right? Nice. But I can take this function and turn it into a table, and then just start typing my money. 1.9 is really close to 2. 1.99 is even closer. 1.999, you can see where it's going, right? Yes? You with me? Yeah? What's the next one going to have? How many nines? 3 nines in it. The next one will have 4 nines in it. There's 5 nines in it. So it's pushing that 0.99 all the way out to the end, right? So 2.9 repeating goes to what number? 3. So very predictable. We should, when we're doing numeric limits, we should check both sides. So like $2.10. Oops. $2.01. $2 and a gas station tenth of a penny. I can see it really, really clear. By the time I get to gas station money, I should see it, right? By the time I get to 3 decimal places. Nice. Let's take a look at another one here. This will be our first algebraic limit. The limit is x squared minus 4 over x minus 2 as x goes to 2 is 4. It's hard to believe it, but we can do this numerically or graphically right away, right? So let's do graphical. Everybody okay with the Desmos? Everybody okay? So my function was x squared minus 4 all over x minus 2. And you could see it looks like a straight line. There is a point at 2, but it doesn't exist. So should have the 0.24, sorry. But that point does not exist on the curve. You with me there? There's an actual hole in the curve there, right? But if you think about when you're walking halfway to the wall, you ever try and cut a piece of paper more than 7 times? A fold, have you done the folding one? Can't fold a piece of paper more than 7 times. They've tried it with a big, giant piece of paper. Same thing with it when you're cutting it. So if you cut it in half and you cut it in half, eventually the paper is the size of the scissor itself. And you can't cut it anymore, right? I think it's 7 times for the folding. I can't remember. It might be 11. So this particular curve has a hole in it, but I can still predict my height. Easy to predict with the graph, right? You could just look at when x is 2. I like doing something like this when I'm discovering x equals 2. Gives me a line, and I can kind of see where the height is there, right? Yeah? I could do it numerically. How would I do it numerically? What would I be putting in at first? Left side. It's getting closer to 2, right? 1.9 again, right? 1.99. 1.999. This one's really obvious it's going to 4, right? So the idea here is I'm going to do some algebra. I'm going to work on the limit as x goes to 2 of star, okay? And so star is my x squared minus 4 over x minus 2 with what? X not equal to 2, right? But that could be manipulated, right? I got x plus 2 times an x minus 2. Again, if you need paper, there's paper at the front of the room here. And this is, right? This is just an x plus 2 with x still not equal to 2. So I get the line x plus 2, but now I can plug into it, right? When I was here, I couldn't plug in. I can get it close and make a prediction. So what did I say so far? If you can plug in, plug in. If you can estimate, right, numerically, fine, do that. And now my third approach is, or if I can look at the graph, do that, right? Not very hard to do, but I want to be able to come up with a replacement function that where I can plug in directly. And that'll come from my formal definition. You'll understand why in a second. But I'm looking at now the limit as x goes to 2 of x squared minus 4 over x minus 2 is the limit as x goes to 2 of star, which is 2 plus 2, right? Remember, this is star. And that's just 4. And there it is. There's a couple of things, subtle little things about the notation. Right? I got my replacement function, called it star. I manipulated it all the way to someplace where I didn't have an issue. I didn't get 0 over 0, right? So if I plug in the negative 2 here, I get 0. Sorry, if I plug in the 2 here, I get 0 here, I get 0. Right? So I'm trying to come up with a replacement function. Once I plug into the replacement function, I'm not using the word limit anymore. Right? How are we doing? We okay? Here we go. Formal definition. What time is it? Oh, good. I know early college has, what do you have your English class next? Right at 11? Is that right? Yeah. So not a lot of time after class to ask questions. And then if there's any kind of extended time for testing, things like that, you got to talk to me as soon as you can. That'll definitely be an issue on test days. So is English Monday, Wednesday, Friday? Here's our formal definition of a limit. The limit, as x goes to c, of f of x equals L, is equivalent to, that's looks like a double arrow, right? Is equivalent to, is logically equivalent. It's not 4 equals 3 plus 1. It's some concept is the same as some other concept, right? For every epsilon greater than 0, there exists a delta greater than 0, such that if 0 is less than the absolute value of x minus c is less than delta, then the absolute value of f of x minus L is going to be less than epsilon. This is the formal definition of the limit. I'll say it again. I'll write it out. Okay? If I know the limit of x goes to c of f of x equals L, and I also know that for every epsilon greater than 0, for every positive number in the y direction, right, like a radius, think of it as epsilon up, epsilon down, there exists a delta in the x direction, okay, this, such that if 0 is less than the absolute value of x minus c is less than delta, if I keep my x values within a restriction so that my y values stay in the restriction, then I know the limit of that. Whenever x minus c is less than delta and bigger than 0, I will guarantee the function minus the limit will be less than epsilon. Oh boy, what the hell's going on, right? So here's my version of it for every dartboard. With a radius of epsilon. Radius of epsilon, yes, you with me? There exists a radius of delta So first of all, do we understand dartboards? Most of you aren't old enough to drinking in a bar, so you might not understand a dartboard. Can you picture the archer shooting the arrow into the big white circle? Yes? In the middle is called bullseye. So we're going to say the bullseye is our limit, right? So if I can get a dartboard and find a radius for the bullseye such that all of my function values that are inside of the bullseye must also be inside the dartboard. If I have values inside of this, so you can see the values, can you see the function values? Say yes. Thank you. So I can see the function value. So I pick my delta, right? So, and I restrict the values within that delta range. In fact, it goes probably from here to here, right? Like the great. My delta goes out a little bit further, right? I'm trying to match up to that width, right? You with me? So look at the blue highlighted parts of the function. Are they still on the board? Good. Remember, it's for every epsilon, right? Every single epsilon. So what am I going to do to the board? Shrink it down to what? To 0. And then what happens with these blue points? Where does it hit? Only on that limit. It goes right through the center of the bullseye. I'm using a program here called Sketchpad. GeoGebra does similar stuff, but is free. Sketchpad is not. Here's my epsilon delta. Oh, this is it. So notice at 2, I'm at a height of 4. You can see my function here, x squared. A to c is my delta. The radius AC is my delta. The radius AB is my epsilon. Okay, you with me? Yeah. So notice the highlighted part of the function. Let me cheat a little bit. So my delta goes all the way out to here, right? Yes, you with me? And my delta goes all the way out to here. So I don't know what happened to my. I gotta fix it. Hold on, sorry. Okay, hold on. So my delta goes all the way out to here. So notice all of this function is not on the board anymore, right? And when I shrink it down, right? No, look at it. Still, this is not right here. This is not on the board. So when I shrink it down to nothing, I don't get a limit. But it's just because I picked the wrong delta. So now, look at my function to here. Nope. Right about to here, right? I'm looking at the left edge of that green inner circle, yes? Okay, now you can see the part of the function that's within my restriction of delta. Oops. With my restriction of delta, which I picked as epsilon over 5 on purpose, because I know the answer already. Within epsilon over 5. So this is a radius of 5, this is a radius of 1. Yes, with me? Yeah. So look at the pieces that are restricted from my left and right movement. All of those pieces from the function are still on the board. You agree? Still on the dartboard. And now when I shrink my dartboard down, is that dark purple still on the board? Yes. This one's not moving with me, but this one's now here, right? Is it still all on the board? Yeah. In fact, it'll stay on the board when I go all the way to that single point, which is my limit. So I guarantee to hit the bullseye. I'll do that again later this week, make it a little bit clearer. Okay, let's do a couple more algebraic limits. So we're going to have 3 algebraic limits. We're going to have to factor. We're going to have to find an LCD, or we're going to have to use a conjugate. All of these processes are finding this replacement function. Oh, by the way, look at this replacement function again. What part about this formal definition says I don't care about getting all the way to C? What part of it says I don't care about getting all the way to C?
It doesn't have anything to do with the...
Exactly. So if I let x go all the way to C, I can C minus C, that's 0. I want it to be bigger than C. So I don't care about getting to the x value. But I want to make sure I can predict the L, right? So what about this is saying left and right? Absolute value, exactly. Absolute value is being like a radius. Right? So the radius in the x direction goes left and right. The radius in the y direction goes up and down. Right? So again, this replacement function is all I care about. Finding this replacement function. Okay. So we did an algebra one. Let's do another algebra one. Let's do another factoring one. Let's see. The limit as x goes to 1 of x cubed minus 1 over x minus 1. Easy to find graphically, easy to find numerically, not so easy to find algebraically. Notice that if I plug 1 into this function, right, what do I get? Zero over 0, right? 0 over 0 is our first indeterminate form, meaning sometimes 0 over 0 will go to 0, sometimes it will go to 1, sometimes it could go to infinity. So we have to kind of discover it, what's going to happen here. If you remember how to factor this, right, I get this, and of course these cancel, so I get my replacement function of x squared plus x plus 1. You remember long division or synthetic division? So I like the synthetic here. If I plug in 1 into 1x cubed, 0x squared, 0x minus 1, I bring down the leading, and then I multiply, and then I add. Oops. And I multiply, and then I add. And I multiply, then I add. And notice I'm getting 1x squared plus 1x plus 1. Right? 1x squared plus 1x plus 1. Do you remember doing the synthetic in pre-cal? Long division in pre-cal? Long division is fine. Long division actually works better. I've got it x cubed plus 0x squared plus 0x minus 1. X times what will get me to x cubed? That's x squared, right? Come back and multiply. I get x cubed minus x squared. Change my signs and add. The first term goes away every time. Rinse and repeat, right? X times what will get me to x squared? Yep. Come back and multiply. I get an x squared minus x. Change the signs and add. And obviously x minus 1 goes into x minus 1 one time, right? So long division, synthetic division, just have your factoring memorized, right? Whatever you want to do. So what do we get for our limit now? This is a limit as x goes to 1 of x squared plus x plus 1. Once I plug the number in, I don't need the limit anymore. I get 3. I got only 2 minutes left. I won't probably have time to finish. Yes, what's up? Okay, so I started with x. Can you come in here? Yeah, so if you look at my algebraic manipulation, my x minus 1 is canceled, and that's all I have left. And that's my replacement function. Right? You with me? Yeah. Yep, and then I'm just plugging into that 1 squared plus 1 plus 1. Yep. I'm not going to be able to finish, so you don't have any homework tonight. You can start reading chapter 2, 2:1, 2:2, 2:3. Yes? We'll finish this on Wednesday. I'll see you Wednesday. I'll be here at 8:30 if you need me. So have a great day. Thank you. Robert, please.